because you're making some judgment, some adjustments, tweaks to it, what you now need to do is follow it up with a traditional finite element. You put the loads on this optimized part, you constrain it the way you want to, and then you ask the question, is this a good design? If you look at the results that it gives back to you and says, gee, the stress levels are really low, they're a safety factor of 8 or 9 on an RC car, what can you do to that adjusted shape that you made? Well, you can thin it down. You can begin to adjust parametrically the thickness or some of the other parameters based on the finite element analysis. And so what we're hoping that you'll do is not just go off and choose different parts, but you would go back to your topology optimized parts and you would say, okay, let's check these things and let's look at them and see if in fact they have reasonable loads. And so to do that, we want to kind of talk about the CAD approach. So the first thing that you need to do is create, create the models and understand the use cases of the models. And so this is something that you should have already done for these topology optimized parts. You should know roughly what the design space is. You should know roughly what the use cases are. And now that you've done some topology optimization, you should have a better understanding of the model itself. So the CAD process, the first thing that you have to do is think about defeaturing your model. More than likely, your model has some edge blends, some fillets, some radii. It may even have some holes in there that you're not too worried about. The holes are attachment holes. They really don't need to be there. We can put a load right at that location. We don't have to have a cylinder representing the screw that goes into it. And so you need to think about defeaturing your model. After you do that, you need to then discretize it with the right choice of element and order. You need to assign material properties, and you need to apply boundary conditions and constraints. Now, depending on the CAD system, the order of these things may vary. Generally, your toolbar is laid out in such a way that the first thing they want you to do is on the left, and the last thing they want you to do is on the right. And so it may be on the CAD system that the first thing they want you to put in is the material properties. And they want you to put that in on the real model, not on the defeatured model. Okay? So don't get too hung up on this order that's listed on the screen. Just realize that you have to get those 4 things accomplished before you can kind of go on to the next step. Okay. The third step is submit your finite element deck. And we refer to it as a deck because when it was 1950s, you did a bunch of punch cards. And the punch cards were the nodes and elements and loads and everything else, and you took this big stack of punch cards over and you handed it to the computer. Well, if you print out, we'll see in a slide here in just a minute, if you were to print out a finite element file, you would notice that it is very 72 characters. Every line is filled with 72 characters, and that's exactly what would be represented on a card. And then the last thing that you need to do is the post-processing, which is really visualize the results, interpret the results, and create a report or report the results. So we're going to kind of step through this. Create a parametric model, and the question is why? Why do you want to create a parametric model? What's the benefit or use of a parametric model in relationship to finite elements?
If it doesn't pass the finite element analysis, you can take them apart
So in my day, when I was doing finite elements on a surface modeling system, there weren't solids at the time. There wasn't this concept of parametrics. Generally, once you made the mesh and went to solve this thing, you had to literally throw away the mesh, adjust the model, and then rebuild the mesh. In today's world, the mesh is associative, it's connected with the model. So if the model gets tweaked, it gets adjusted in length, it gets adjusted in thickness, generally the mesh will update and refine itself. So, good point. Other comment?
I was thinking possibly advanced first you optimize the basic shape, right? And then you optimize size.
Size and shape.
Possibly be the reason.
So generally speaking, the way Altair approaches it, they want a parametric model once you get into the size and shape, because all they're doing is saying adjust this fillet size, adjust this length, adjust this thickness, and they're wanting to work with parameters. So, all right, a little kind of note on pre-processing. Where should the pre-processing be done? Should it be done in Siemens? Should it be done in CATIA? Dassault? Should it be done in Altair? Should it be done in MSC software? Should it be done in ANSYS? What is the pre-processing? Well, it's the defeaturing, it's the meshing, it's the loading, it's the materials, it's all that stuff. Where should it be done? Where could it be done? Well, it could be done in any of these, right? Any of these systems could do the pre-processing. Okay. Is there a reason why you would want to do it in the CAD system as opposed to over here in ANSYS or in Nastran? Well, we just kind of talked about it. The pre-processing in many of these systems is associative, and so as I change the model, it'll automatically change the mesh and things like that. Okay. What if I choose to do it inside of a world-class pre-processing system like Altair? Altair's claim to fame is we are the best pre-processor. We're the best mesher in the world for structural meshes. There's better meshes for CFD. What if our company decides this is where they want it done? Is that a good choice? Well, do we lose associativity? We do, but we can write routines inside of here that basically will map the process on any new model. So if a new model comes from Siemens down to Altair, from Dassault up to here, and if that model looks very similar to one that we just did, all you have to do is say, take this surface and swap it out, take this one and swap it out, and the meshing parameters can update and be maintained, but it takes a little bit of effort to build that link. It's not automatic. It's automatic over here,